Hi students, I'm Praveen Sebastian Paul. In this lecture, we are discussing the biasing concepts of PN junction diode. So previously we had mentioned what is a PN junction and how the PN junctions are formed. And here we are discussing the biasing concepts. A PN junction connected to an external voltage source is called a biased PN junction. Such a PN junction finds a variety of application in electronics. By applying an external voltage, the width of the depletion region and hence the current flow through the PN junction can be controlled. There are two ways of connecting an external voltage source across this PN junction diode. They are forward bias and reverse bias. Firstly, when it comes to the forward bias, in forward bias, the positive terminal of the external voltage source, that is a battery connected, is connected towards the P region, and the negative terminal of the voltage source is connected to the N-type region. So this is shown in this figure, and this configuration reduces the width of the depletion region, that is a VB is reduced, and thus a large amount of current flows through the junction. In practice, to forward bias a PN junction and to conduct a current, the external applied voltage should be greater than the barrier potential of the diode. So as we mentioned earlier, the barrier potential for silicon is 0.7 volt and germanium is 0.3 volt. Thus, the applied voltage should be greater than this barrier potential based upon which type of semiconductors are we using. So second one is the reverse biasing condition. In reverse biasing, the positive terminal of the external voltage source is connected to the N-type region and the negative terminal of the voltage is connected to the P-type region of the diode. So this is shown in this figure, and this configuration increases the width of the depletion layer and no current flow through this junction. However, at room temperature, a small amount of current flow through the reverse bias junction due to the availability of minority charge carriers. This current is called the reverse saturation current, and it also increases with the increase in temperature. So now we are discussing in detail about both of these forward and reverse bias condition. Before that, if we are increasing the reverse bias to a large value by increasing the applied reverse voltage, the depletion layer breaks down abruptly and large amount of reverse current starts flowing through the junction. The applied voltage at which the abrupt current flow occurs is known as breakdown voltage. This is represented as VBR. So my dear students, now we are discussing in detail about this forward bias and reverse bias condition. In forward bias, a positive voltage is applied to the P-type side with respect to the N-type side of the junction. With a voltage applied in this way, the hole in the P-type region and the electron in the N-type region are forced towards the junction. This reduces the width of the depletion layer. The positive charge applied to the P-type material repels the holes, while the negative charge applied to the N-type material repels the electrons. The distance between the electron and the hole decreases as they are forced towards the junction. This lowers the built-in potential barrier. With increasing the forward bias voltage, the depletion layer eventually becomes thin enough and the built-in electric field can no longer counteract the charge carrier motion across the PN junction, consequently reducing the electrical resistance. The electrons which cross the PN junction into the P-type material will diffuse in the near neutral region. Therefore, the amount of minority diffusion in the near neutral zone determines the amount of current that may flow through the diode. Only the majority carriers, that is the electrons in the N-type material or holes in the P-type material, can flow through the semiconductor for macroscopic length. With this in mind, consider the flow of electron across the junction. The forward bias causes a force on the electron, pushing them from N side towards the P side. With the forward bias, the depletion layer is narrow enough that the electron can cross the junction and are injected into the p-type material. However, they do not continue to flow through the p-type material indefinitely because it is energetically favorable for them to recombine with the holes. The average length an electron travels through the p-type material before recombining is called the diffusion length, and it is typically on the order of microns. Although the electron penetrates only a short distance into the p-type material before recombining, the electric current continues interrupted because the holes begin to flow in the opposite direction, replacing the ones that the minority carriers electron recombining with. The total current is constant in space because any variation would cause charge to build up over time. So the flow of the hole from the P region into the N region is exactly analogous to the flow of electron from N to P region. Therefore, the macroscopic picture of the current flow through the diode involves electrons flow through the N-type region towards the junction and holes flowing through the P-type region into the opposite direction towards the junction, and the two kinds of carriers constantly recombining in the vicinity of the junction. The electrons and the hole travel in opposite direction, but they also have opposite charges, so the overall current is in the same direction on both sides of the diode as required. So this is the forward bias condition. Now we are discussing the reverse bias condition. The reverse bias usually refers to how a diode is used in a circuit. If a diode is reverse biased, the voltage at the cathode is higher than the anode. Therefore, no current will flow until the electric field is so high that the diode breaks down. Because the p-type material is now connected to the negative side of the applied voltage and holes in the p-type material are pulled away from the junction. This causes the thickness of the depletion layer to increase. Similarly, because the n-type region is connected to the positive side, the electron will also be pulled away from the junction. Therefore, the depletion layer widens and does so increasingly with increasing the reverse bias voltage. This increases the voltage barrier, causing a high resistance to the flow of charge carriers, thus allowing only a very small electric current to leak across the junction. The strength of the depletion layer electric field increases as the reverse bias voltage increases. Only the electric field intensity increases beyond a critical level. The p-n junction depletion layer break down and the current begin to flow, usually by either the Zener or avalanche breakdown process. Both of these breakdown processes are non-destructive and are reversible as long as the amount of current flow does not reach the level causes the semiconductor material to overheat and cause thermal damage. This effect is used to one's advantage in Zener diode as a regulator for electric circuits. The Zener diode has a well-defined low reverse breakdown voltage by design. A typical value for the breakdown voltage is instance of 6.2 voltage. This means that the voltage at the cathode can never be more than 6.2 volt higher than the voltage at the anode, because the diode will break down and therefore conduct if the voltage gets any higher. This effectively limits the voltage across the diode. So my dear students, these are the biasing conditions for a p-n junction diode. So as we mentioned, a biasing condition means we are applying an external voltage towards this p-n junction, and there are two types of biasing, namely forward biasing and reverse biasing. So my dear students, hope you had understood this topic. So my dear students, kindly write down this assignment question. Our question is, write detailed notes on this biasing condition of PN junction. So my dear students, in the upcoming lecture we will discuss the different characteristics of this PN junction diode. So dear students, see you soon. Until then, goodbye, thank you and all the best.